To wrap up chapter 2, we're going to look at multiplication and division of whole numbers. And these notes are the longest in terms of the length of the PDF because I have a lot of examples. And we're going to start with multiplication. And I have several ways that multiplication can be introduced and described. And we're going to start with multiplication as repeated addition. And I even have the definition of multiplication as repeated addition, because that's really what multiplication is. It's a shortcut for repeated addition. In the image here, there are 5 groups of 4. So with addition, to find the answer, how many total little pinwheels do we have? It would be 4 plus 4 plus 4 plus 4 plus 4. But instead of writing that out, it can get a little tedious. We just use multiplication. We have 5 groups of 4, so 5 times 4. So again, great way to start. Multiplication is just repeated addition. There's also array models, and this is good with manipulatives. Here we've got little bean counters. And the array model is handy when you are showing the commutative property. If you have 5 rows and 8 columns, 5 times 8, you've got 40 little beans. But if you demonstrate it slightly different, where you have 8 rows and 5 columns, it's still going to equal the 40 beans. So again, this is really good for showing that commutative property. Order does not matter when we're multiplying. Similarly, maybe a little more abstractly, you can use the rectangular area model. So here, if you have tiles, you could set out a rectangle with one side of length 4, the other side of length 6, and how many tiles is it going to take to cover that rectangle? That's the area. So you're also introducing area of a rectangle. Further, there is the skip count model for multiplication. So here, to show 3 times 5 is 15, you can skip count by 3s. 3, 6, 9, 12, and 15. You've skip counted 5 times. The next one is a little more abstract. Probably you'd want to use this with some upper level elementary age kids. And this is a multiplication tree model. This is something that's used even at the college level when we are showing counting outcomes, especially in terms of probabilities. So what we have here is a demonstration of 4 times 3. So you'll notice on the bottom there's the flags. The 4 represents the different colors for the top flag. The top flag could be red, yellow, green, or blue. And if the top flag is red, yellow, green, or blue, you have the same 3 choices for the bottom flag. The bottom flag is going to be one of the other 3 colors, yellow, green, or blue, if red is the top. If yellow is the top, you have red, green, or blue for the bottom. If the top is green, red, yellow, blue for the bottom. And if blue is the top, you have red, green, yellow for the bottom. So how many different flag patterns are possible here? 4 times 3, 12. And again, this can lend itself into the idea of permutations when we get into probability. So if you're going to introduce some sort of probability alongside multiplication, that is really handy to have. And finally, I have the Cartesian product Cartesian product model of multiplication. So here we've got types of cones. You could have a sugar cone or a waffle cone. And then there's flavors of ice cream. So we've got vanilla, chocolate, the M can stand for mint, and let's call the R raspberry, okay? So you could have a sugar cone with vanilla ice cream, or a sugar cone with chocolate ice cream, and so on. And you can see you have 8 possibilities. Now here we have the variables representing the different types of cones and the flavors. If you're using this with kids, you might want to actually write out the full words so it's not quite as abstract for them. But this is called the Cartesian product model. And here I have the more formal definition. And this says the Cartesian product of sets A and B, written A times B, just like we're used to seeing, is the set of all ordered pairs whose first component is an element of set A, the second component is an element of set B. So when we're taking set A times set B, we end up with these ordered pairs. The value in the first value in the ordered pair comes from set A, second from set B. And then if we deal with the cardinality of the sets, it says let A and B be whole numbers. Suppose that set A and set B are sets for which small a is the number of elements in set A, small b or lowercase b is the number of elements in set B. Then if you take lowercase a times lowercase b, so the number of elements in each set is going to equal the number of elements in the Cartesian product of those two sets. Now, if this part seems, maybe a little bit overwhelming for young children, it is. These two definitions are not something that you would be introducing to a third grade class. You would not be introducing probably to most high school classes. But I do want to show you the mathematics behind what we might be looking at. Okay, so I'm trying to give you a little bit of behind the scenes, behind the curtain there. And the last thing that I have here in terms of all of these notes and definitions and things are some theorems for multiplication. Just like addition, there's the closure property. If you multiply two whole numbers, the product is going to be another whole number. I've already mentioned the commutative property. Order does not matter. The associative property, that's when you're dealing with parentheses. You can move the parentheses. It's not going to affect the final product. Then there's the multiplicative identity property. If you multiply something by 1, you're going to end up right back where you started. Multiplication by 0, you all know this. If you multiply anything by 0, you're going to get 0. And then there's the distributive property. If you have A times, and in parentheses B plus C, it's the same thing as A times B plus A times C. And it works if the number being multiplied is in front of the parentheses or if it's in the back. The distributive property is still going to work. In the next video, we're going to look at some examples using these properties, but I feel like this is enough for one video, so I'll come back and we'll actually use these properties.